Namaste everyone. Welcome to Ray Optics class. We have seen many types of phenomena of light, including reflection, refraction at plane surface, including normal shift, lateral shift, total internal reflection, optic fibers, total reflecting prisms, then things like scattering, refraction at the surface, Earth's atmosphere, twinkling of stars, sun appearing red and sky appearing blue, all the reasons, the beautiful creation called light, what it will do in the nature, everything we have seen. Now we will move on to the refraction at the curved surface. Reflection at the curved surface we have seen, like mirrors, convex mirror, concave mirror, what happens to the light when it falls on it, that we have seen. Now we will go on to refraction at curved surface. What happens to a ray of light when it falls on the curved surface? Suppose you have a test tube filled with water. What will be the position of the speck of dust inside? Where it will be seen? Where will be the flowers like arrangement inside the paperweight? Where will be they seen when viewed from the curved surface? So what is the image position in the case of curved surface? We will take a single curved surface. Suppose you take two curved surface, it will act like a lens, and that will be a different thing. That will be the next study of this refraction at curved surface. So you have to be ready with pen and paper first of all, because we are going to draw a ray diagram, and for that we want to have a relation which connects all the object distance, image distance, refractive indices and everything. So take a pen and paper, be ready with your pen and paper, and keep on drawing the diagram as I do. So first of all, let me consider a glass rod like this. Don't draw this now. Suppose I take a glass rod or bottom of a test tube, it will appear like this curved. Suppose this is completely filled with water. This is a refracting medium now, right? So bottom of a test tube which is filled with water will act like this, or a glass rod with its end face curved like this, and if I can take the midpoint of this curved surface as a pole, and this curved surface will be a part of a sphere and it will have a center. Even though it is parallel here, this is a curved part and this will be a part of a sphere, this is the center. Join this is the principal axis. So this is pole, this is the center. Now suppose if I switch on a bulb here, the image of the bulb should be formed somewhere else, because when the light from here passes like this and like this, somewhere it should go in and meet the this ray and an image should be formed. Where will be the image of this object formed inside the that sphere? So suppose you take a paperweight and switch on a torch, where will you see the torch inside, and where the image will be formed, where the rays go and meet inside the that glass sphere. So that is the question now. So using that we will derive an equation. So very important derivation, and if you understand the derivation and understand the idea of the final formula, you are going to carry it for the next derivation, that is called Lensmaker's formula. So you have to understand it very clearly. Even for the application of problems, this should be very, very clear. Because just a dry formula will never help you. You should understand the concept behind it, and you have to understand what the terms are in the formula. So shall we start? I hope you are ready with pen and paper. You take the pen and paper and be ready with it. And always we will follow the same method, same definitions. Let the ray of light start from left side and move to the right side. Let it move along the positive x-axis. So in order to do so, I'll take the curved surface like this. This is a curved surface, right? That may be a bottom of a test tube, as I told earlier, or it may be a curved glass rod like this, and let this be this you need not draw like this. This is a part of a sphere. This diagram is not, this dotted line is not needed. It will have a center, right? Because center is needed. And this is the midpoint of the whole aperture, geometrical center, and I call this as a pole and I will call this as the center. Now the curved surface is ready. I'll call this as AB. Just to have an imagination, I have drawn the curved surface, I have completed it. So it is like this, right? So curved surface is taken, and I will consider one object here. The line joining the pole and the center, principal axis. Now, and for convenience, let me keep it as it is. You need not draw this curved surface, okay? Now, so this is finished, right? Now this is a point object or a bulb, say. From the bulb, different rays of light go backside, front side, everywhere. they enter the curved surface also. So after refraction they may meet here somewhere. The image of this point source of light or a bulb will be formed inside. Where is it? That is my question. Okay, now for the time being I'll take that this is immersed in some liquid, say this is having a refractive index N1. Suppose this is kept in this glass rod or a test tube is kept in air, of course N1 becomes 1. And the absolute refractive index of this medium, say this is N2. It is made up of glass or water, whatever it is. Okay, now if you take two rays of light coming from the point source or object, one ray I will consider like this, one ray of light moving along the principal axis, it passes undeviated. Why, sir? This ray of light is incident normally on this surface. Sir, how do you say that it is incident normally on that surface? Very easy to say. What do you mean by incidence normal? Normal incidence, ray of light should go along the normal. When the ray of light is incident on the surface like this, if you want to find out the angle of incidence, all your definitions go as it is, there is no change. Angle between the incident ray and the normal. Where you have to draw the normal? Normal drawn at the point of incidence to the surface like this. How do you draw a normal to the a sphere? You draw a line such that it passes through the center. This is not a normal, so I have to draw the normal like this. This is a normal. How to draw a normal here to the surface? Is this a normal? No, it doesn't pass through the surface. Center. This passes through the center. This is for this one, this is the normal. So if I want to find out angle of incidence and refraction here, I have to draw a normal like this. That means this ray is incident along the normal. Angle of incidence is 0. Angle of refraction is 0. It passes undeviated and moves through the center. Now did you come to know that it is a ray passing through the center, and that's why it passes undeviated. So it should pass through. Take another ray of light. I will take one more ray of light coming from the same object. Let it be incident like this at some angle. Let another ray of light be incident at some angle like this. Now what should happen to this ray? Now it is moving from one medium to another, a medium of say lesser refractive index to a medium of higher refractive index. Let us assume like this. Say this is air and glass. Ray is moving from rarer to denser medium. Its speed decreases. In the optically rarer medium, its speed is more. In the optically denser medium, its speed is less. When its speed is decreasing, it should bend towards the normal. When a ray of light moves from rarer to denser medium, its bending is towards the normal. So if it bends towards the normal, what is the original direction? Original direction is like this. You know it, right? This is the original direction. If it has to bend towards the normal, we have to draw the normal at the point of incidence. Here. How to draw the normal at the point of incidence to this surface? Join this line to the center, right? You have to join this to the center. A line joining to the center will be the normal line at the point of incidence. So like this way. Does it look straight? No, I think. So I have to draw a line like this. Yes, this is the normal. So shall I draw this as normal? Of course, here normal is along the light itself. Here normal is a line which joins the point to the center. Okay, that is a normal line. Okay, now this is the incident ray and a second incident ray. There are many rays coming from the object because it is a point source of light. It is like a bulb. So this is one ray. Suppose there was no medium change, it would have moved straight. Now it should bend towards the normal. That means it bends like this and meets this color, this light, and this is the formation of image here. Here is the image I call it as image. So two rays of light coming from the object O. One ray moving along the principal axis, incident normally, moves without deviation and moves in. Another ray of light, incident at some angle, and if you want to know angle of incidence, draw a normal, a line passing through the center. After refraction, bends towards the normal and meets the principal axis at I. I is the image. Now if you want to write angle of incidence and angle of refraction, go along with your definition. Angle between incident ray and normal, angle of incidence, right? Angle between incident ray and normal. What about angle of refraction? Now you see how is the definition helping you? Incident ray normal, refracted ray and normal, like this. At this point normal is this one, angle of refraction. Now this original direction is not needed for me. Of course, if I want to measure the angle of deviation, this is needed. This is the angle of deviation from this one. It is the original direction and final direction, but for the time being it is not needed. So angle of incidence and angle of refraction we have written. Okay, now I will drop a normal from here, and this I will take it as, okay, I will write this as m. This is n. I don't write pole, I write m and n, of course. Sir, where is m? Whether m is this one or this one, that is both are m. Okay, this is m and this is also m. This is over this one. Actually these two rays should be very, very close to each other. What do you mean by that? If you consider this as a curved surface and this is the principal axis, one ray along the principal axis passes undeviated, another ray incident very close to the principal axis like this one, so that all these angles are very, very small. So if the center is somewhere here, if you draw a normal, then this angle is very small, undergoes refraction, and instead of moving like this, bends towards the normal and meets the principal axis, and all the things, and angle of refraction is small. All these are called paraxial rays, rays which are very close to the principal axis. In that case, if you draw a normal here, won't this point fall on the m itself? So m and n, this point are one and the same if this ray is very close. But in the diagram I can't show it, because I have to draw so many things here, I have to mark so many things, so it becomes difficult. That is why I didn't mark them all, and I didn't take the ray of light very close to the principal axis, but it does mean that it is very close. All these angles are very, very small. So consider a refracting surface whose center is here. Consider an object from the surface at a distance u, object distance is this one. The ray of light is moving from left to right, that is positive x-axis. One ray of light incident along the normal, that is along the principal axis, passes undeviated. Another ray of light incident at some angle I. If you want to find out the angle of angle of incidence, draw a normal, that is a line joining to the center, that forms the I. After refraction, this is the original direction, bends towards the normal and passes and meets the principal axis at I. Angle of refraction is the angle between refracted ray and the normal. Normal is again the same. This is the angle of refraction. And since the ray is this n is very close, and this is not different from this one, this line will be falling over this one when this ray is very close here. Okay, this is the diagram you have to draw. Refractive index of the outer medium is n1, inner medium is n2. n1 is smaller, n2 is greater, so ray is moving from rarer to denser medium. Object distance is from object to the pole. Radius of curvature is from center to the pole, and image distance is from pole to the image. Okay, and now my job is to find out the relation between n1, n2, u, v and r. I have to connect all these things, the four or five things. Refractive index of the medium outside, refractive index of the medium inside, object distance, image distance and r. Now you just be prepared with the sign conventions. Same sign conventions hold good here also. All the distances are measured from the pole, and distances measured along the direction of light are taken positive, opposite to the direction of light are taken negative. So if you take such sign convention, you will find that only this one is negative, u is negative. When you start from pole, you have to measure the object distance towards the left side, so it is negative. All the other things are positive. Radius positive, image distance positive. So positive, this is positive, this is positive, this is negative. That you can remember. Okay, now I have to connect all these things. Finally, what formula I should get, I'll write it now only. It is a another thing. Sir, how do you differentiate n1 and n2? It's the best way is, n1 is the refractive index of the medium where incident rays are present. This one. I'm not saying object is present. Incident rays are present. Medium where incident rays are present, its refractive index is N1. Medium where refracted rays are present, its refractive index is N2. So you should stick on to all these decisions so that it will not direct you in a wrong way in any of the problems. So if you are very confined with all these definitions and the way in which you understand, everything holds or goes in a nice way when you solve the problems, when you apply it in another derivation and all. Otherwise it will be a full confusion and it will mess up everything. So N1 is the refractive index of the medium where incident rays are present. N2 is the refractive index of the medium where refracted rays are present. Even in a new derivation, N1 and N2 are changed with the NO and NI, something like that. You shouldn't get confused. So N1 is the medium refractive index of the medium where incident rays are present, these two. N2 is the refractive index of the medium where refracted rays are present, these two. Okay, now the formula goes like this. Final answer: refractive index of the medium where incident rays are present minus object distance plus refractive index of the medium where refracted rays are present divided by image distance is equal to refractive index of the medium where refracted rays are present minus incident rays are present divided by radius of curvature. This is the formula. Finally you get it here. So refractive index of the medium where the incident rays are present by negative of the object distance. Refractive index of the medium where refracted rays are present by image distance. Then the image refracted rays present medium refractive index minus the refractive index of the medium where incident rays are present divided by radius of curvature, N2 minus N1 by R. See how this will be useful in the next derivation in the problems later. Simply if you by the formula in the problem and in another situation N1 and N2 may be interchanged, so it shouldn't divert your idea. So it should be very firm. Okay, so how to get this how to get this equation? What you can do is you can take of course it looks like he say here one Snell's law, you know, N1 sin I is equal to N2 sin R. Snell's law is obeyed in all refractions, whether it is curved one, plane surface, prism, whatever it is. Refraction formula holds good everywhere. That is Snell's law. N1 sin I is equal to N2 sin R. R is here refracted ray and normal. Normal is one which passes through center. So if you want to use this formula N1 sin I is equal to N2 sin R, of course this contains N1 I R, because when angles are very small, and already I have told this ray is this pink ray is very close to the principal axis. If it is very close, then I and R everything will be very small. Then I can write N1 I is equal to N2 R almost, because when theta is small, if theta is small, you know sin theta is almost equal to theta, and even tan theta is almost equal to theta. Sin theta and tan theta are very close to each other. For example, sin 0, 0, tan 0 is also 0. So when they start the 100-meter race, sin theta and cos theta were together in the beginning. As the angle increases, tan theta overtakes, because tan theta has to reach infinity when it comes to 90, whereas sin theta has to reach only 1. So sin theta and tan theta are almost equal to theta when theta is very small. Okay, these conditions you must know. So if you are going to use this formula finally, then you should have I and R, because this final answer is not in this form. There is N1, there is N2, there is U and V, but we have I and R. So convert these angles into U and V. That is your job. So you must have the idea how to derive the relation. Otherwise what happens is in between you will be stuck and you will forget what to do. What is the next step? I don't remember it. So you must know why this final formula is got, and what is the way in which you have to go in order to approach this. That's why I put all these things in between. Now we will start the derivation. Okay, we will start it. Finally you should get this one. Okay, I have to connect I and R, because we have N1 sin I is equal to N2 sin R. When I and R are very small, N1 I equal to N2 R, because sin I is almost equal to I, sin R is almost equal to R. N1 I is equal to N2 R. Now replace this I and R with U, V, radius and all. How to replace? We will take, even tan theta is almost equal to theta, we know it when theta is very small. So we will start, I think I can write it here, no problem. Okay, we will write it here. start taking, I want both, you have to look into both diagram as well as derivation, both. You can't leave one. So now, we will take this. Can you see this angle I? Angle I is the exterior angle of the triangle, that is NOC. In this triangle NOC, this is the exterior angle. Can you see that? What are the interior opposite angles? While selecting interior opposite angles, you must be very careful. You shouldn't select the interior opposite angles as you like, because you see, which angle is the exterior angle? This one. But this angle is made from this triangle, right? This one and this one, not from this triangle. It is a different line, it is a refracted ray. This normal is going like this triangle. So in the triangle NOC, I is the exterior angle and these two are the interior opposite angle. Do you agree that? Right? It is not this one, because the triangle shouldn't go like this and like this. It should go like this, because this is the exterior angle. So in the triangle NOC, we will write, in triangle NOC, right? Exterior angle I is equal to sum of the interior opposite angles, NOC plus NCO. NOC plus NCO. Am I right? These two angles. NOC plus NCO. It is only in the triangle NOC. This is the exterior angle, because this side is produced backwards and this one. Sum of the two interior opposite angles. Now, how to fill this NOC and NCO? We will take tan, because this is a right angle triangle here. This is a right angle triangle here. Take tan NOM. Okay, NOC and or NOM I can write. It is one and the same. NOM and NCM. Okay, angles. It is same. Instead of putting NOC, I will stop it at NOM and NCM, so that later steps will be easier. What is NOM? We will take tan NOM, which is almost equal to NOM. Why? Because tan theta is almost equal to theta. When this ray is approaching very close to the principal axis, like this way, somewhere here, then theta, I, R, everything will be small. So tan NOM will be very small, tan, not tan NOM, I have, okay, tan NOM is equal to opposite side by adjacent side, right? Tan NOM is equal to NM by OM. And you know, M and these 2 points are similar. They are one and the same points, because when this ray is very close, this line will fall over this edge. Tan NOM is equal to NM by OM. Am I right? Tan NOM, opposite side by adjacent side. What is tan NCM? Tan NCM, which is almost equal to NCM, because tan theta is almost equal to theta. What is tan NCM? Opposite side, NM by MC. NM by MC. So let me write M here if you are too much confused, right? Tan NM by MC. Okay, then. Okay, so I, for I you can write it now. I is equal to, then we can write angle of incidence I is equal to, substitute it here, NOM, NM by OM, NM by OM plus NCM, NCM is NM by MC. This is equation 1, because we are going to put this equation in N1 sin I is equal to N2 sin R, however, later. Okay, that is one equation is over. So if you want N1 sin I is equal to N2 sin R, you should get R also. So shall I write for R? Where is R, sir? R is here. In which triangle R is found? NCI. It is found in NCI. And in NCI, it is not exterior angle, right? It is one of the interior angles. So I will take this also. This angle plus this angle. Sum of the interior opposite angle to this one. Am I right? In the triangle NCI, this one, NCI, this triangle, in that triangle, this angle R plus this angle NIC or NIM, this plus this, interior opposite angles is equal to exterior angle. So shall I write that R as angle R in triangle NIC, interior angle R plus interior angle NIC must be equal to exterior angle NCM. So what is R? Because we are going to substitute in N1 sin I is equal to N2 sin R. We want I and R, right? Because sin I is almost equal to I. Sin R is almost equal to R. So what is R? Angle NCM minus angle NIC. So that is the difference. Okay? Now R is equal to NCM, angle NCM. Okay, we have to get this now. We will take tan NCM as we did here. Tan NCM, we are ready with tan NCM, which is equal to NCM. So we have it here. You can use it here. But we don't have NIC, angle NIC. And it is also equal to NIM. Am I right? Tan NIM and NIC are equal. So what is tan NIC, which is equal to tan NIM, almost equal to NIM, is equal to, because angle tan theta is almost equal to theta. Tan NIC or NIM, this angle is equal to, in the right angle triangle, opposite side NM by adjacent side MI. NM by MI. Is it okay? So tan NIC or NIM is equal to this angle opposite by adjacent. NM by MI. So let us substitute this in the equation for R. So if you put this here, R is equal to NCM, which can be brought from here. NM by MC minus NIC. NIC is NIC is NIM. NIM is NM by MI. NM by MI. Is it okay? Tan so R is equal to NCM. NCM is NM by MC. NIM is NM by MI. So we have got equation 2. So we have got I, we have got R. Now it is your job to put them in N1 sin I is equal to N2 sin R. Then you will get all these relations. So shall we proceed? I will rub this now for the time being. This one. That's not needed for me. Okay. Now I will apply general law of refraction. Okay. This is B. Yeah. Apply general law or Snell's law. N1 sin I, N2 sin R. N1 sin I is equal to N2 sin R. N1 into when sin I is almost equal to I, sin R is almost equal to R. When I and R are almost same, sin R is almost equal to R. So what happens to this above formula? N1I is equal to N2 R. Sin I is almost equal to I. Sin R is almost equal to R. N1 into, what is I? We will go back to that. I. Nm by OM plus Nm by MC. So shall I take Nm outside now only? So whole board is available for you now. Nm into, I will take Nm outside. 1 by OM plus 1 by MC into, that is equal to N2 into sin R. What is sin R? Sin R is almost equal to R. What is R? R is Nm by MC. There also you can take Nm outside. Nm into Nm by MC, Nm by Mi minus. So 1 by MC minus 1 by Mi. Okay? Nm gets cancelled. So it gets cancelled. Now, so now if you rearrange this, or we will multiply it, cross multiply it, and cross multiplied answer I will write it here. Here I will write it. N1 by OM, N1 by OM, okay? N1 by MC plus N1 by MC, N1 by OM, N1 by MC equal to N2 by MC, N2 by MC and minus N2 by Mi, N2 by Mi. Okay. Now, you club N1 and N2 together. What you will get? N1 by OM and N1 by MC. So, they are together now, no problem. Or, okay, I will bring this N2 by Mi here and remaining here. MC and MC I will club it together, because MC is that is radius of curvature. So, if I put them together, shall I rub this here and I will write it here. So, I will continue this here. This is not needed for the time being now. Okay, we will put it here. Yes. What do you have now? N1 by OM, N1 by MC. I brought N1 inside, and MC and MC you club it together. You bring this one to the right hand side, left hand side. So what you will get? N1 by OM. If you look into the final answer, you will come to know what you have to do. N1 by OM this one minus N2 by Mi, minus N2 by Mi. Right? No, this is plus, right? This is minus. By the time it reaches here, it will be plus. N1 by OM plus N2 by Mi is equal to, this is plus. What about here? N2 by MC minus, this becomes minus N1 by MC, right? Now you substitute the values. You substitute the values of OM, Mi, MC, MC, they are all distances. Now with the sign conventions, use the symbol. Hope you are looking into the diagram also. We will substitute the values. N1 by U. This is OM is U, but it is minus, right? So minus U plus N2, refractive index of the medium where refracted rays are present, divided by Mi. Mi stands for this one, image distance. It is plus V. It is not minus, but object distance is on the other side, is equal to this MC can be taken common, MC common. What is that? Radius of curvature, left hand side positive, sorry, right hand side positive radius, N2 minus N1 by R. So I will write it like this now. Hope you can see this now. Up to this, you have to remember the formula like this way only. Don't by heart the symbols, you just remember the formula like this. Refractive index of medium where object is present, or incident rays are present, not object, where incident rays are present, medium of incident rays, divided by negative of object distance. Of course, you need not write this in the examination, just to know the idea behind it. Refractive index of the medium where incident rays are present, divided by negative of object distance, plus this part, refractive index of the medium where refracted rays are present, okay, divided by image distance is equal to, what is the other hand? It is N2 minus N1. Refractive index of refractive index of medium where refracted rays are present, minus, I want still some more space, refractive index of the medium where incident rays are present, N2 minus N1 divided by radius. You will come to know the seriousness of this understanding, because you will have to apply it in a very proper way in the problems as well as the next coming derivations. So yeah, you must remember this. This will come automatically then, like a chain. So refractive index of the medium where incident rays are present, my negative of the object distance, refractive index of the medium where refracted rays are present, divided by image distance, plus refractive index of the refracted medium minus refractive index of the incident medium, divided by radius of curvature. That is a very important formula, and this formula is going to help you to solve many problems. So we will use this in different cases to understand the formation of the image. We will use this to derive the lens maker's formula and in many cases. But what the diagram you have drawn, you should go theoretically, you shouldn't by heart it. By hearting is a very bad habit here, because there are more chances of going wrong. And all the definitions, angle between incident ray and normal, refracted ray and normal, everything has to be followed in an exact manner. Whatever you have studied earlier, it should be put as it is, all the sign conventions and all, finding the normal and writing the Snell's law. It's a very simple derivation with a small knowledge that you have to apply Snell's law, n1 sin I is equal to n2 sin r. But when all these are very small angles, sin I and sin r is equal to I and r. So find out I and r using tan theta formula, tan I, tan r and all. So I and r will be got, then substitute it. So very easy derivation. Now, how to use this? Suppose you take a simple problem like, I'll rub this now. Suppose you are asked to find out, suppose I have a sphere like this. I will explain it now for the timing, or like this. Suppose you have a glass rod. You have an object here at a distance of say 5 centimeters, and the glass rod is of radius of curvature, say r is equal to say some 10 centimeters. Where will be the image formed? That is the question. So an object, point object, is kept at a distance of 5 centimeters from the curved surface of radius of curvature 10 centimeter and refractive index 1.5. This is r, so refractive index is 1. Where is the position of the image? So r is given, u is given, refractive indices both are given. What is the form? Where is the image formed? So how is the formula? Formula is like this: refractive index of the medium where incident rays are present, negative of the object distance, plus refractive index of the medium where refracted rays are present by image distance. Refracted rays are present, incident rays are present by radius. That's what you have to do. So this is how it goes. n1 by minus u. What is n1? The medium where incident rays are present, 1. Minus u again it is minus u. You have to substitute, because this formula, once it is derived with sign conventions, but this is derived for this convex spherical surface. In another problem or another situation, the spherical surface may be like this, or spherical surface may be in different way. In that case, can you apply the same formula? Yes, possible. Even though this formula is derived for this type of spherical surface, this formula is suitable for any spherical surface, because apply the sign convention once again, then it is applicable for any type of surface. So you need not restrict only for this condition, it can be applied to anything. So even for this condition, apply the sign conventions once again, you will get the correct result then. So what you will do, this is object distance, this is minus in the formula itself. What is object distance? It is minus 5. I'll keep all the centimeters as it is, minus 5, plus refractive index of the medium where refracted rays are present, 1.5. By image distance, don't know whether it is plus or minus, don't know. According to the situation, we will get plus or minus. That may be minus also, it need not be plus only always, we don't know. Image may be formed somewhere else also. So that is equal to refracting medium minus incident medium by radius. Radius is on the right hand side, it is plus only, it is 10. You have to solve this now. So what is the answer? This is 1 by 5, or shall I, okay, I will write one more step. 1 by 5 plus, because minus of minus, 1.5 by image distance is equal to 0.5 by 10. You see, this is 0.5 by 10. So shall I write 0.5 as half? If it is half, it is 1 by 20. Am I right? It is 1 by 20, and if I continue this problem here, I'll continue to here. Okay. Now, 1 by 5 I will take to the other side. 1 by 1.5 by V is equal to 1 by 20 minus 1 by V. 1 by 20 minus 1 by V. So 1.5 by V, image distance, is equal to, sorry, 1.5 by V is on the other side, 1 by 5. 1 by 20 minus 1 by 5 is equal to 1 by 5 by V. So 20 I will take it common denominator, 20 ones are, 5 fours are, right. So that is equal to minus 3 by 20. So what is V? So minus 1.5 by V is equal to minus 3 by 20. So there is a chance that image is formed on the same side. So I will explain why did we get V negative. So we are going to get V negative. Bring V here, 20 here. 20 into 1.5 is 30. 20 into 1.5. 3 comes to this side. 20 into 1.5 and minus 3 here, that is equal to V. So V is minus 10 centimeters. Sir, why did we get minus? In the derivation, we got the image distance inside the glass sphere and we got it inside. So now we got it negative. What is the problem? Very simple. This ray of light, according to the position of the object, sometimes may bend so less that, and the ray of image will be formed somewhere here itself. It will be formed on the back side itself, back side of the object itself. Of course, I have to draw a ray diagram very sensitively here. Suppose this is the center, the ray of light will bend in such a way that, suppose this is the position of the object and the ray of light is incident like this. The ray of light will bend towards the normal, of course, but the bending will not be, this is the original direction, bending will not be enough so that it will meet this ray. Another ray is going like this. This ray bending towards the normal is correct, no doubt, it is bending towards the normal, but that type of bending, that amount of bending is not enough to converge and meet this ray, right? So again, this ray appears to be coming from this side and this is the image. So object is formed behind the this one, negative x-axis. That is possible. So that is why it is minus 10. So this is how we will do it problem, and later on we will take few more problems, then we will come to know how it is done. Okay, so for the time being today we will stop it, and we will come along with a few more problems and different types of surfaces in the later classes. Now study the derivation, right? That is very important derivation. So hope you will do that. Thank you. We will meet in the next class. Thank you.